G'day everyone, Richard Walding here. Just going to run you through some slides of a presentation I did at Griffith Uni, the Gold Coast, in November 2021. Here's the slide that I use. That's the title slide down there, so you'll get an idea of what's going to happen. Just make that bigger. I've titled it Rolling Balls and Stacked Magnets because I'm doing this in two parts. The first one is the rolling balls one is to do with inclined planes, and the second one is to do with magnets and magnetic fields. So I'll do it in two parts, and I'll make two separate videos for YouTube for this because they go for a fair while. Okay, look, the whole purpose of the presentation was to present a couple of student experiments that really work. The problem is, for a lot of teachers, students will suggest to them some good ideas about experiments that they'd like to try, and if a teacher hasn't been through that particular experiment the student's talking about, you never know whether it's going to work or not. So I've chosen two things to look at, and I think you'll find these experiments are pretty good. So let's get started. The first one I've called Rolling Ball. So this is part A. This is to do with inclined planes. Okay, so in the Queensland syllabus, the physics syllabus, there's a number of suggested and mandatory pracs that students can do. In this first topic, now this is Unit 3 for the general syllabus. One of the topics is to do with inclined planes, and there's an experiment, a suggested experiment in there. So this is the suggested one. It's to do with the parallel component of the weight of an object down an inclined plane. You change the angles. Now there's a few experiments in that topic, the topic of motion and gravity. There's one on projectile motions, there's another one on centripetal forces, and so on. But I'm just choosing this one because it's one students will have been introduced to in their Year 11 course or Unit 2 course, and they might decide that this makes a good follow-up. But again, the teachers will probably do something like this in the Grade 12 course or the Unit 3 course. Okay, so there's the objective of that, or the suggestion about the practical. Okay, now the way most teachers would do this in class, there's a few different ways you can do this. This is a common one. Now this is one I've put in my textbook, the Oxford textbook. I've called it experiment 1.3, even though the syllabus doesn't give numbers to the experiments. So what we're looking at is a parallel component of a weight down an inclined plane. Now what I've got here is a fairly simple setup, just a inclined plane. Now I use, you can use a piece of chipboard or something fairly stiff. You don't want it to buckle in the middle, so you need it fairly stiff. And I've used a collision trolley there. It's about 600 or 700 grams, let's say 0.6 of a kilogram. And I've got a thin string over the top of a pulley. Now this is a frictionless pulley, well, as frictionless as we can get, and some brass masses hanging there to provide a weight to counter the force down the incline. Okay, so the forces acting on this are the force down the incline, okay, where you can see I'm pointing down the incline, parallel to the incline. Now you'd call that FP, F subscript P, or F with a little parallel sign. Okay, so either would be okay. Now you know that's equal to FW, the weight of the object, times sine theta, where theta is the angle. Okay, so that's what you're trying to basically prove, that the force down the incline is equal to FW, which is equal to mg, so mg sine theta. So if you keep this at rest or at constant speed, the force up the incline should be equal to the force down the incline. Okay, now the force up the incline is provided by the hanging weights here, the brass masses or whatever you're going to use. Now, The way the experiment works is you'll set that at a particular angle, let's say 10 degrees, and you'll adjust the hanging masses until the collision trolley just starts to move up the incline. Okay, not accelerate, but just barely starts to move up the incline, and you'll record the mass, the hanging mass, and convert that to a weight in newtons. Then what you can do now to adjust that, you can use either little paper clips, or I use steel washers. You just get some steel washers from Bunnings and put them in a little cup hanging off there, and you can adjust the hanging weight or the mass fairly easily. Okay, the second thing you want to do is to then take some of the masses off and wait till the collision trolley just moves down the incline, just starts to move. Okay, and then the average of those two masses will be the mass required to provide a force to keep that at constant speed, or at least keep it in position on the inclined plane. Now, the good thing about that experiment is that in one case you've got the trolley just moving upwards a little bit, so the force of friction is down the incline, and in the second case you've got the trolley moving down the incline, so the force of friction is up the incline. Okay, so when the trolley moves down, the friction force is up, and when the trolley moves up, the friction force is down. So the two friction forces cancel out because they're in opposite directions, and you get a nice little experiment. Here's a picture of a girl or a student doing that experiment at my school. Now you can see there's the inclined plane. It's just some chipboard, just from Bunnings. It's a 1.2 metre length, 300 millimetres wide, and I think they're about $4 or $5. A frictionless pulley, well, it's as frictionless as you can get. A piece of light cord over that. Now the cord is called it's called lightweight and extensionless. So in other words, it doesn't expand. It's not rubbery, and it's as frictionless as you can between the string and the pulley. And there's my little hanging bucket. You can see in there's some nuts and washers and brass masses and all sorts of things. So the student just adds washers to that cup until the trolley moves up the incline, then takes some out until it just moves down the incline, and each case you weigh the bucket, the little bucket. Okay, now you can adjust the height of the incline by using this laboratory jack, or you can just slide the jack in closer and that'll lift it up. You've got to be careful though, if you slide it right in, this can get too heavy and it'll tend to topple. And the other thing students find is that as you increase the incline, so you make it much steeper, this little string touches on the edge of the bench, and that confuses them for a while. So just point that out. You need to make sure that the inclined plane has plenty of overhang. So that's the main part of that. So that's a good way, a good little experiment that works well. Now remember, that's the suggested experiment. This is not the student experiment, which is derived from it. So this is just out of the textbook. It's a suggested experiment in the syllabus. Okay, another way of doing it, here's the results from that. Now this is just taken from my students' work from last year. So you plot mg sine theta down the bottom. Now as theta increases along the x-axis, mg sine theta increases, and there's the hanging weight up the side. Okay, that's just in newtons. And now that it should be a 1:1 graph, because what you're trying to do is to illustrate that the hanging weight, the force up the incline, is equal to the force down the incline. So you're just basically proving that the force down the incline is mg sine theta, which is in the formula book, and you're just trying to prove that basically. Now you'll notice the blue line, which is the average, is 1:1. You can see here at 2.5, 2.5. Okay, but there's my data. Now I've got error bars. The error bars are there because the force up the incline will be when the weight is a bit higher, and the force down the incline, when the trolley moves up the incline, the weight will be a little bit higher, and when the trolley is just moving down the incline, the weight will be a little bit less. So you've got an error bar for each of those readings, and there's the line of best fit, the trend line, the blue trend line through the middle, and then I've got the maximum and minimum lines of best fit as well. And they fit between the error bars, and then I've got the formula for the trend line. Now you'll notice that's pretty close to 1.98, and the R squared value is high. You want that as close to 1 as you can get it, which indicates that the trend line is a good fit for the data. Okay, so that's a neat little experiment. So that's what you might have done as the suggested experiment, and we want to take that a bit further. But look, before I go on, here's another simple way of doing that suggested experiment. All it is just an incline plane. Now I've just used a chunk of aluminium. You can see, I'll just go back and show you what it looks like. This piece of aluminium is just, you can see that? I've cut a bit off. It's that aluminium on the screen, but I've just cut a bit off so I could carry it around to the Griffith presentation. But that's a nice rigid piece of aluminium. But you could use, a piece of pine or something like that, fairly stiff. What I've done is I've just used this board that's on there is just a piece of pine. You can see it there, a piece of pine with a hook in it. And I've used a couple of pencils as the rollers, so to try and minimize friction. So that is a neat little experiment. So by changing the angle, the scale reading on the spring balance will change as well. And to provide limited or low friction, the pencils tend to roll, and I'll show you that. I've made a little video, and you can just change the angle and you get different readings. So here's a little video I made, and just watch it. So I just give it a tap, it oscillates a bit, comes to rest, and you just get a reading off the screen balance, off the spring balance rather. So if you look here, there's the reading. What is it, about 0.46 or something like that? Oh, here we are, I've written 0.45. You're really trying to take plus or minus 0.05. That's the scale reading. Okay, the uncertainty in the scale reading. Okay, let's move on. Now here's a graph of mg sine theta versus the scale reading in newtons, and you get the same sort of straight line. It's roughly 1:1. You can see I'm getting a value there for the gradient of 1.0, so that works really well, almost goes through 0. Now it doesn't matter that it doesn't go through 0, because that gives you a bit of systematic error for the students to talk about why it's not through 0, and they can talk about maybe the contribution of friction and so on. Now you do that with error bars and all sorts of things, and that's a good little experiment. So that's the suggested experiment. And what you want is something that comes out of that, that the students can modify. Now before I get on to modifications, here's a third way that you can do, and I've seen a lot of schools do this. I do this as well, but as a demo. It's just looking at the acceleration of an object down the incline. So I've got the aluminium track. Now if you're using the laminated chipboard, it'll have that surface, the plasticky surface, which is fairly low friction. But what you want is something to slide. Okay, we're not really interested in rolling friction with this, so you don't want anything with wheels. And that's why if you have it moving and it's got wheels, you've got to take into the rotation of the wheels. Now with the previous one I used the pencils, but they were hardly moving, so that was fine. In this case I'm going to let something slide down the incline, and so I want to have low friction, So what I do is I've polished that now just with a scouring pad and get it nice and smooth, because from I use it year after year. We bought a lot of these year after year, and it does oxidize a bit over the subsequent year. So you just get a scouring pad and a bit of water and wash it off, and then you need to oil it up a bit. And I just use this stuff here. I'll show you a video of it in a minute. Photo. It's just the silicon-based lubricant, WD-40 silicon lubricant, and that seems to work really well. Just put it on and rub it in. Okay, now I'm going to let a plastic cup, you'll see in a second, 5.9 grams. It's just low friction plastic on a silicon surface. The length I'm going to let it go down is 50 centimeters, and I've got it at an angle of 25 degrees at the moment. So here we go. Look, just put it on, let it go, and measure the time. Now the time taken from that line down to the bottom, a distance of 50 centimeters, it's 0.617 of a second, and I've been able to work out the acceleration from that. Now, I think in the next slide I've got the calculation. I'll just have a quick look. Hang on. Oh, there's the WD-40, by the way. Just the silicon lubricant. Okay, so I'll just go back, and you can see, I'll just run through this again. There it goes, down the incline. Now those two, that data there, it's travelled 50 centimetres in 0.617 of a second, so you can work out an average velocity. Now to get the final velocity, you just double that, because you can assume the acceleration is uniform. So you get the final velocity, and the acceleration is just v minus u on t. So v is that final velocity, which is twice the average velocity, minus u, and it started off at rest, so that's minus 0, divided by t, and you get the acceleration. Then you can repeat that for all different angles. And the problem is measuring this time. Look, it's a nightmare trying to measure that with a stopwatch, but I'll come to methods about that, but let's assume you've measured it somehow. Okay, so here's my graph. Now in this case, what we're looking for is a straight line, and you can see it's fairly straight, bit of a curve, but when you put error bars on that and do it properly, I mean, I rushed through this just for some data, but what you'll notice is that the trend line cuts the x-axis at here about 0.14 or something like that, 135. Now if you convert, that's sine theta, if you convert that back to an angle, it's about 7.9 degrees. So what it's saying is that when it's 7.9 degrees, the acceleration is 0. So in other words, it moves at constant speed. It's not accelerating, it's either at rest or at constant speed. So in other words, it needs 7.9 degrees of slope before it's got sufficient force down the incline to overcome friction. Okay, so wouldn't it be good to minimize friction to get that intercept way down here? And by using polished low friction surfaces, you could do that. Okay, so the gradient is 9.92, you can see from the formula for the trend line. And if you're interested, the coefficient of friction, mu, now I know this is not in the syllabus, and it says you don't have to be able to do calculations on mu. This is going back into Unit 2. It talks about it, just so long as you can understand what friction is and how it's measured. But mu is just the tan of the angle. So it's tan of 7.9 degrees, and it's 0.14. So it's a really low coefficient of friction. But you know, one of the lowest you'd get. But you probably can get that lower in the classroom if you can get some Teflon, some little cart made out of Teflon, a piece of Teflon or a Teflon surface. That's how you do it. Okay, now comes to the main point of the talk, which is to get an experiment that students can use for their student experiment. Now that's the assessable part, also called the IA2. internal investigation or internal assessment number 2. And the internal assessment says you need to identify an experiment to modify. Now, by the word modify, we mean to extend, refine, or redirect. Okay, now those 3 words mean something in the syllabus, and the teacher, or you'd explain that to students what they mean. Okay, I won't really do that. Now, extend means to really extend the range of the variable. So you might have, instead of doing from 5 degrees to 10 degrees or 15, you might go up to 30 or 40 degrees. So you could extend that, or extend the distance it's done over. Refine is to refine the experiment by using a different timing apparatus, or to do more duplicates, or something like that. Redirect is really where you're looking at a different variable. You're still using an inclined plane, but you're redirecting it to look at something a little bit different. And you'll see in a minute I'm going to talk about redirecting. Okay, so these are the what I think we'd say here is that we've considered sliding motion, and we're going to consider rotational motion as well now. So we're going to talk about a rolling ball, and that was the heading I gave for this talk. Okay, you'll also need to provide justifications, justified modifications. And I think what you could do is say something like the parallel component of the force, of the weight of the object, does provide translational motion, and that's the sliding sideways motion, but you'll also get rotational motion if you've got a ball. So the work done is a combination of the translational kinetic energy and the rotational. Now, this is a bit different to what students would have covered in class, but this is just a student experiment that I know works, and students will might find it interesting. And lastly, the research question, and I'd suggest something like that. Basically, you're talking about a rolling sphere. So the students, I mean, this is only a suggestion, and the students would have their own research question. After all, they get marked on that. Okay, so that is a redirect. Up the top, I said there are three types of modifications. Redirection is where you change one of the variables. So we're looking at the type of variable. So we're looking at changing it to include rolling motion. So that's a redirection. Okay, let's move on. Here's a diagram for what I'm the experiment. This is really taken out of the Unit 2 Oxford book, my Unit 2 book, or Unit 2 section of the first textbook. There's an experiment where they're just measuring not so much the acceleration down an incline, but learning how to plot velocity versus distance. And that's in the general syllabus. It's in the Year 11 course in Unit 2. Okay, and I've got an experiment in the back of the book which looks at that. Okay, so here's me doing it. The whole purpose of me doing this for this presentation that you're watching is that we know that acceleration of a sliding object is uniform, okay, because after it slides down the incline, friction is constant, or you assume it's constant, and so it accelerates at uniformly. Okay, so the question is, will it accelerate uniformly if it's rolling? So what we need to do, just to show you, and this is not a part of the experiment, but this is just so that you, in your own mind, you know that it's uniform. So I've taken a steel ball bearing. I'm going to let it go from 60 centimeters, measure the acceleration, and then try it at 50, 40, 30, and so on, and keeping the angle constant. Now, there should be a relationship that shows the acceleration is constant. In other words, the gradient of a curve, when you plot the right curve, you should see it being a straight line, or linear really, and directly proportional. Now what I've got here is a steel ball bearing. It's about 20 millimeters, well 16 to 20 millimeters, doesn't really matter. Now I just made up a little aluminium, or a little like a hook really. The problem students have is if they hold it with their fingers, when they let the ball go, like this, they open their fingers and let the ball go, and the ball tends to stick to their fingers because you've got a little bit of moisture on your skin, and so you don't get a clear, clean starting position or starting motion for the ball. And what students tend to do is to pull it backwards at the same time. Now I don't know why, but they do, and so the ball actually starts off moving backwards, which is even worse. So not only does it stick, but as the student moves their hand away, it tends to pull it away as well. So I just made up a little simple hook, but it's not foolproof. Look, I'll just show you this working. So I move it out of the way and it rolls down. Now I've measured a couple of things here. The distance down the incline is 60 centimeters. The time it took, 1.1 seconds. Now I measured that using a stopwatch, but I had a video included of the, actually I used my stopwatch program on an iPad and just included that in the film. So the final velocity is just twice the average. Now the average is 0.6, which is s divided by t. So 2 times the average gives 1 meter per second. Now that's the final velocity down at the bottom of the incline. Okay, so let's have a look at how that works out. Here's the formula you use. Now this is straight out of the formula book. V squared equals u squared plus 2as. U is the starting speed, so it's 0. So v squared equals 2as. So if you plot v squared versus s, you should get a straight line if acceleration is constant. So let's plot v squared versus s. If we get a straight line, direct proportion, which going through the origin, that'll confirm that acceleration is constant. So there it is there. Look, now that's just done from one set of data. Now I didn't do error bars. I just did this quickly just to get some data to use in this presentation. So there's the displacement up the incline along the bottom, okay, going from 0 up to 1 meter. Now that aluminium track I used was 1.2 meters long, and if you're getting stuff from Bunnings like the laminated chipboard, it's 1.2 meters long, and you get stuff that's about 30 centimeters wide, about $5. And you can see the velocity squared. Now what you'll see there is the gradient is 1.265. Okay, so that gradient is 2a. So the acceleration would be 0.63 something like that. Here it is here, 0.633. Okay, so what I've confirmed there is that the acceleration of a rolling ball down an incline is uniform. Okay, so if there's any question that it mightn't be uniform, and that way you're able to say the final velocity is twice the average velocity because it's uniform velocity, uniform acceleration. So that works pretty well. Okay, so here's a sample of my track that I'm going to use for the rest of this. Now I've got the same ball, that's this ball here, if you can see it. I'll just show you that ball there. It's about something like 20 millimeters in diameter, but it doesn't really matter what size you use. But I'm going to talk about size now. I just wanted to talk to you about the tracks. Now you'll notice there's a flat track. That's very much the same as just using a piece of aluminium, flat aluminium like that. I've also got this curved track here. Now I was demonstrating that at Griffith Uni. Here's a piece here. Look, I'll make that big so you can see what's happening. You can see the curved track. It's Okay, it's from Bunnings. You buy lengths of that track. It's about 1.2 meters. No, 1 meter length, about $4.80 or something like that. So it's a curved track. I'll show you Bunnings' catalogue entry for that in a minute. But you could also use this. Now, I wouldn't suggest you do this, but just a piece of, here we go again, just a piece of channel, aluminium channel from Bunnings, about $4 or something for a meter, and it's 1 centimetre by 1 centimetre by 1 centimetre, and the ball sits there in the track like that. So here the contact point is, is very small. Actually it's not quite as small as the flat. It's a little bit wider, but it's, for all intents and purposes, it's pretty much just a single contact point. Here you can see the contact points are really tiny, so much lower friction. But this is a real problem, and I'll come to that at the end. Okay, now the balls that I'm talking about, if you can see them here, whoa, I'll just change the video so you can see them. Okay, so these balls, you can see, are just stainless steel balls from this place I've got mentioned down here. Okay, go to this. Now that's in Brisbane at Mansfield. I just rang them up. You can look at their catalogue online. I just rang them up and said I'm coming out, and they had all the stuff ready for me. That was just to save the $17 delivery. So if you're not close to Mansfield, and you'll have your own. You'll be able to order those wherever you like. You can get them from science supply companies, but I wanted them in a hurry, so I just, for this presentation, so I just ordered them and went out and picked them up, saved $17. And the big ones, look, they're $11.60 for the great big ones. That's the biggest one here. You can see it's pretty big, and right down to the tiny ones. So you just need a variety. I'd say the something around about 20 millimeters works really well, and you'll see why in a minute. The track is from Bunnings. Doesn't matter which you get, it's all much the same sort of price. Okay, there's the Bunnings. That's aluminium crescent, it's called. It's a curved track. One teacher rang me up and said she couldn't find the aluminium track on Bunnings. It just doesn't show up as curved track. You have to actually call it crescent track, but now you know. Okay, so that's good to have. Okay, now what I'm going to do here is just see if there's any difference between those three types of track: the flat, curved, the curved is the crescent, and the channel, which is the squarish one. Excuse me. Now I've got a little piece of aluminium here. I've got the three balls all the same. I've got the flat track there, the curved track, and the channel. They're all at 80 centimeters. I'm going to remove, and it's 5 degrees for incline. I'm going to remove this piece of metal, which is holding them back, and let them roll down. Now, if it didn't matter which sort of surface you used, they'd all hit the bottom together. Now, I'll tell you in advance, when I made this, when I lifted this up, I made the same mistake that students do. I didn't lift it up cleanly. Now, I could have repeated that and videoed it again, but I thought I'd just show you how simple it is, or how easy it is to not let them go evenly. So just watch this. So I'll just start it, and now watch, I'm lifting it up now, but see what happened? I twisted it by accident. I just twisted it as I lifted it. And so the balls start off unfairly. The channel one is started off at a disadvantage. But what you'll notice is that the balls, even though there was a slight delay in that last ball, the other ones go down together and the gap gets wider and wider between that one. So we can say the curved incline and the flat incline, the balls hit together. Look, there they are there, hitting together, and then the one on the other track takes a little bit longer. Now, I'm using the iPad as the timer. Now, each frame on the iPad's 0.03 of a second. Right? It runs at 30 frames per second, so each frame is about 0.03 of a second. And if you watched it, you could see it goes from 0.41 to 0.44. I'm just moving that by one frame. So each frame is about 0.033 of a second. Okay, so you'll notice that two balls hit there, and the other one, that's at 0.58. It takes 1, 2, 3, 4, 5, 6 frames, which is about 0.18 or 0.2 of a second to get down there. Okay, so what I've done, hopefully, there is to demonstrate that you can't use the channel if you're comparing. Well, it will be different. You'll have a slightly different formula for a ball rolling down the channel than you would having it rolling down a flat incline. But the crescent incline is good. The whole purpose I use the crescent is that because with the curve, the ball tends to sit in the curve, and when it goes down, it doesn't roll off. If you're using the other things like this, as the ball goes down, it moves around. It's not as good. Okay, so let's move on. So what I'm going to do now is compare the different diameters. I'm going to use a 5, 10 and 15 millimeter ball. So here's the 5. It's a little tiny one, obviously right up to this size, which is the 15 millimeter ball. Now what you can see on the screen is I've got a little T apparatus again, and that's holding the 3 balls. Now I'm using the curved track in each case, so I'm keeping that the same. So let's see what happens when I let them go down, and here we go. Okay, now you'll notice they all hit the ground together, so I'll just go back and check that. So they're coming down evenly. Look, they're all the same, and bang, they pretty much hit the stop at the end. Now you'll notice the little tiny one at the furthest from us took a fraction of a second later, but it's less than a frame of the iPad timer, so we can say that there's no difference between those 3. Okay, so let's move on. Let's now try the 15, 22 and the 27. Now the 27 is getting up much bigger. You know what it looks like. So this is the 27. Okay, so we're going to compare the second range of those, and I'll let them go through, and sure enough, they all hit the ground at the same time. So here they go. Look, down, 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 bang, hit the stop at the end at the same time. So those 3 are the same. Look, 1.535 seconds for all. Okay, so let's now try the biggest and the smallest. So I've got the little tiny one, which is the 5 millimeter, and I've got the great big one, which is the 35 millimeter. Now let's see if they go down together, and here we go. And pretty much they do. Now if you look, I've said there the times are, look, that's about 2 frames different, about 0.6, roughly about 0.6 of a second, 0.06 of a second difference. So I'll just go back and have a look at that. They're coming down pretty much the same now. Now the big one just gets ahead of the little one, and then bang. Now I'll see how much longer it takes. So there's about 1, 2, maybe 2 frames extra to get to the bottom. So there is a little bit of difference with the little tiny one. Now the reason for that is that if you look at this channel close up, it does get little pits and things in it, even though if you clean it properly. Now any bumps or irregularities in the surface of the curved one, or any surface really, will have a bigger impact on the tiny ball because relative to the diameter of the ball, it's much bigger. So my suggestion would be avoid that little tiny one and stick to things like 15 to 20. They're a reasonable price and they give good results. Okay, now there's several ways you can measure this velocity. There's 5 that I can think of. Now the first one is using a stopwatch. Now I've written there hopeless. The stopwatch, not for a student experiment, you want something better than a stopwatch. And I think if you use, videoing the videoing stopwatch is a different thing. But if you're just trying to use a stopwatch, when you think about it, the reaction time is about 0.2 of a second. So that when you're talking about times of 0.6 of a second, that's a horrific amount of reaction time and uncertainty. Now, don't let me stop you from, I shouldn't suggest that you don't use a stopwatch. I use a stopwatch to measure the times for a tennis ball falling from different heights. Okay, it's good to introduce the students to the limitations of the measuring instruments, and I do it with a stopwatch. But for the student experiment, I use something I think is better. So that's the video. I was showing you before the video of the iPad, and you can get that, and that has a frame rate of 0.0, or the frames about 0.03 of a second between them, so you're getting some good times. So that works well. Another one is using Logger Pro or some other video analysis program. Now I use Logger Pro. You have to buy that, but there's a free one called Tracker you could use, and schools will have all sorts of things. There's DataMate and various other types of programs. Now you make a video using your phone or a camera or whatever, and you import that into your video analysis program, and you can measure the times accurately. Now you could do the velocity as well, but for the purpose of this, I'm just getting the times from it. Fourth way is to use a photo gate, and I'll show you that later. It just is a little gate at the bottom of the incline, and the ball cuts a light path. The photo gate measures the time that the path is cut for, and if you know the diameter of the ball, you can get the velocity, or the data logger will work out the velocity for you. Lastly, we can do the horizontal range. Now this is a neat little way of doing it. It works really well. Many teachers use this anyway. So let me explain how it works. I'll show you the diagram for it. So basically what you've got is the ball on an incline, and it's sitting on a bench top, and there it is at the edge of the bench. Okay, the bench is SY, that's the height of the bench, and that's the vertical displacement between the edge of the bench and the floor. And so as the ball rolls down the incline at angle theta, it comes off there and then becomes a projectile and has a curved path and hits the floor there. And that distance Sx is the horizontal range. Now, what you're trying to do is work out V, the final velocity at this point here. And you know V is in the horizontal direction, is V cos theta, that's the component. And in the vertical direction, the component of that V is V sine theta. Now, the time for the time in both cases is the same, obviously. It's the one object. So you can get the time in terms of vertical displacement and the time in terms of the horizontal displacement, and you can let them be equal, and you can end up solving for V. So let me just show you that. It's pretty straightforward. There's the horizontal range. Sx equals horizontal velocity, which is constant, times t, and I've replaced the Vx with V cos theta. So you've got that formula there, and rearrange t equals Sx, the range, over V cos theta. Now in the vertical direction, the vertical component uses this formula. Now this is straight from the formula book. The vertical displacement is equal to the starting vertical velocity times t plus a half gt squared. So I've replaced the uy with v sine theta, because that's the relationship with the component. Uy, or the vertical component, is v sine theta. And we get that. Now I then replace t, the time here, with this value up here, sx over v cos theta, and there I've put it in there. Okay, and I've done it here for the time as well, squared. Now the sine theta over cos theta here becomes tan theta. The v there and the v there cancel out, so you're left with sx over tan, or times tan theta. And here you've got a v squared on the bottom and a cos squared theta on the bottom, and an sx squared on the top. Okay, now you can rearrange all that to get v squared as the subject equation. You get that. V is just the square root of that. And here's an example. For 5 degrees, the vertical height is 0.736, so that's a bench is 73.6 centimetres high from the floor, and the distance, the horizontal range for the ball when it hit the ground is 0.26, and you can solve that and get 0.65. So going back, that horizontal range enables you to work out the V. Okay, oh, well, you know the vertical height as well. Okay, so here's a little demo of one. Look, I've just got the ball there at 50 centimetres. I'm going to let it go. It's going to roll down the incline. It's only a shallow incline, 2.5 degrees. Now that's good because it gives you a fairly reasonable time. There's the light gate. It'll cut through that light gate. I've got the light gate velocity will register on this LabQuest data logger. I've got the iPad there to measure, so I can look at the video to work out the time. And I've also got a piece of paper on the floor. The ball will leave the end and then go down like that and crash onto the floor somewhere here. And I can measure that horizontal range on the floor. Okay, so that's how it goes. Letting it go, there it goes, bang, hits the floor. Now I can just stop, go back a bit. You'll see here's the ball coming down. It cuts the light path. You can see the light coming on and then off. So the data logger measures how long it took to go through there, and then it falls as a projectile to the floor. Bang, crashes there and bounces. Now that'll leave an imprint in the paper, which I can mark. And you can also get a time off the iPad. Okay, so time 1.835 seconds. I've worked out the final velocity from the data logger, and the displacement on the floor is 0.2 of a metre, so it must have been somewhere here. Okay, so let's do it again. Now I'm changing the angle to a much higher angle, steeper angle, so it should go faster. Previously it was 1.8 seconds. Let's see what happens here. Bang, really quick. Okay, 0.6 of a second, and you saw where the ball hit. It was quite low, quite a fair way out. Go back. Through the data logger, look, there's the light going on and off, and bang, it hits the floor there. Okay, so I would have put a mark on the floor, pen mark on the floor where it hit. And you can see I've got all my other previous readings for the different angles drawn on there as well. Okay, so let's move on. And now there's an example of the data logger. Look, it's given me the time through the gate, and it's worked out a velocity 1.6 meters per second. Okay, there's my piece of horizontal paper, or paper for the horizontal range, and you can see it makes a little dint. You can probably see some cases. Look, you can see the dint there. Here's a dint in the paper. I've just used a piece of like felt on the floor just to enable the ball to make an impression. That works really well. Okay, so there's the relationship. Now we know it's we can double the average velocity to get the final velocity. Now this V is really VF, the final velocity. we know acceleration is uniform, so we can do that. The formula from the formula book, v squared equals u squared plus 2as. Instead of u, I've used 0. There's the 2 for the constant there. The acceleration, oh sorry, I'll do this again. The v squared equals the acceleration, which is, no, this is not, oh, it's 2 times 0.5. The 0.5 is the displacement down the incline, 0.5 of a metre. So 2 times 0.5 times a, that's that formula there. Now notice I chose 0.5 of a metre for the incline because that works out to 1 and makes the maths nice and simple, but you don't have to. You can make it any size you like. Okay, now here's my my graph of the 3 different methods. Now down the bottom I've listed the Logger Pro, which is the blue one. Now that's where I've used a video analysis to get the time. I've also used the gate, the light gate at the bottom of the inclines, the orange, and the horizontal range on the floor is the grey. And you can see the lines, they're all parallel pretty much. The blue one in the middle, the Logger Pro, is basically the average of the other 2. So let's have a look at a bit of analysis for this. Now I've done the gradient or the formula using Excel. It gives me the formula for the trend lines. You can see the dotted trend lines there. And they're all around about 7.7 to 7.3, 7.4. And now the student, excuse me, the student would only do one of these. You run out of time trying to compare the 3. So you just do one. And now let's have a look at, well, that's the relationship, you'd say. The acceleration down the incline, which is a measure of the force, is proportional to sine theta. And basically you're confirming Fp equals mg sine theta. So that works really well. And what's the accepted relationship? Well, let's have a look. This gets a bit tricky, but a ball that's rolling down an incline has 2 types of kinetic energy. It's got the translational, which is just moving in a sideways down the incline. You've also got the rotational, the spinning motion here. Now you're familiar with the EK translational, it's just a half mv squared. The rotational, the formula, now this is not in the syllabus, and it used to be done in senior syllabus, senior physics a fair while ago. Not so much these days, but it's a half times I, which is the moment of inertia, and there's a formula for that, times omega squared, and this is the angular velocity, which is in radians per second. In other words, the rate of spinning. Okay, formulas are pretty straightforward. So you've got the potential energy of the ball at the top of the incline is equal to the final translational kinetic and rotational kinetic. Okay, so EP is just mgh, EK is half mv squared, and EK rotational is half I omega squared. Now, I is 2/5 mr squared. That's the formula for the moment of for the inertia of a solid sphere. 2/5 times the mass times its radius squared, and omega is the angular velocity, which is the velocity, linear velocity divided by r, and that really is in radians per second, but it's squared as well. Now the m's cancel out and we're left with gh equals a half v squared plus this. Now the half of 2/5 r squared becomes 1 on 10 r squared. Oh, 2 5s are 10. Oh, sorry, no. Yeah, that's right. V squared. So the next line, half v squared plus a half 2/5 r squared times v squared on r squared. Now the r squareds will cancel out and you're left with 2 on 10 times v squared. So that's this thing here. And you can add them together and you get 7 on 10 v squared. So v, if you rearrange that, is square root of 10 on 7 gh. Okay, so here's an example that I got. I've just substituted the values into this, and at 5 degrees from 60 centimetres up the ramp, which would have a height of 5.2 centimetres, we get a theoretical velocity at the bottom of the ramp of 0.85. Okay, and that's the velocity. Now, to work out the acceleration, use the formula relating VU and ANS. It's that one. U is 0, of course. So A is v squared on 2s, and s was 0.6. So it's 0.85 from here squared, and you get 0.602. The acceleration is 0.6. So theoretically, the acceleration, the gradient of the graph should be 0.6. And here we are here. There's the theoretical value there in orange. So you can see how close the blue one is to the orange, but all of them are pretty close. If you had error bars in there, you'd really notice they all overlap. Let's have a look at the relationships. Okay, and again the gradient is all the same. And here we have the slight differences between the gradient values and for each of the different methods compared to the theoretical, which should be 7. You can see they're pretty close, and the R-squareds are really nice. But of course you'd have error bars on whichever one you had. Now you wouldn't, like I said, you wouldn't do all three types. You'd do theoretical and one of the other measuring types. Okay, now in theory the gradient should be 7, and that's what we're getting here in theory. Look, here's the formula. I've rearranged it, and you end up with A on sine theta equals 10 over 14 times g, and you can rearrange that to get the gradient. That's the gradient. It comes to 7. That's just the theory behind it. And there it is there. They should all be 7, so you can work out the error. Well, here, look, I'm interested in this x-intercept. That gives you a measure of the friction. So that's the uncertainty. So the students should relish getting some uncertainty because it's something to talk about. But if you calculate the uncertainty from these intercept, and I've actually worked out the x-intercepts for each one of these. It's not hard. And you can see the angle that it cuts here would be 0.2, a very low angle. That's a measure of the friction, really. The limiting friction that is needed, or the limiting force that is needed before it'll start to roll. And you can see the different methods give you different calculations for that that slight angle that's needed. That's a bit of a measure of the error, really, in the experiment. Okay, and you can do the error analysis of the gradient. So it's just the error percent, the percentage error is the observed value minus the accepted value over the accepted value. And here's for the linear, the log of pro, there's my value from the graph minus the accepted value 7 over the accepted. It's about 3.76% error. And then for the gate, about 5% error, and the range 1.13. You can see that range one gives you quite an accurate value, so it's quite good. They're all around about 5%, all less than 5% really, or pretty close to it, and that's why we can say if the error is less than 5, considered accurate. But that's only within the limitations of the testing equipment, really. Okay. Now, lastly, just to finish off, now I wouldn't suggest you do this, but it's some student might want to do it, and it does work really well. But when you're talking about a ball rolling down a channel, the contact points are these two little points here and here somewhere, there. Okay, and the radius of rotation, the ball rotates around that distance there, r. Now you can work that out from Pythagoras' theorem. R is the square root of the hypotenuse r, the radius of the sphere, minus the base there, which is, we call it w, the width of the track. So it's w on 2. So that's r. Now, basically, you're just resubstituting into this formula, but instead of r, you've got this little complicated thing here. And you can see over here, it's basically the same formula as before, but instead of 2/5 mr squared, it's now 2/5, and I've got a complication added in here. And you can see I've done the r squared minus w on 2 squared. That's this thing here in place of that r. Okay, so what if it ends up with a messy formula. You can't really get it any simpler than that, or I couldn't. And you end up with v squared is equal to 2gh over 1 plus this fraction here. Okay, so you can actually calculate the theoretical value, and you can measure the your experimental value as well. Okay, so here's my results. The observed value was 0.99 of a second, meters per second. Theoretical was 1.04. Now you could do your error analysis on that, work out the absolute error and the percentage error. Look, it's only 5%, and that's really good for a laboratory experiment. Okay, I'm going to finish there. That's the end of the rolling ball part. If you want the slides to go back over those in detail, if you go to my senior physics site, if you scroll down, you'll find something that says 2021 rolling balls and stacked magnets. Now that'll have the link to the YouTube video that you're watching, but it'll also have underneath it a link to, so you can download the PowerPoint slides, and it's about 450 meg. Oh no, it might be about 250 meg now for that. Now, for the Griffith Uni talk that I did, I then went on and did the stacked magnets. Now, I won't do that now. I'll make that as a separate video so that you can go to each one separately. So the same thing is, if you're looking for the stacked magnets one, you'd go down and you'd find this link down the bottom. One will be for the rolling balls and one will be the YouTube video for stacked magnets, but the PowerPoint will be the same. So that's where you'll look for that. So I'm going to sign off now, and if you want to see the stacked magnets one, just go there and we're all done. So that's it. So all the best. Bye.